So I'm going to have a situation so I can put the charge in the furnace, heat it all up to high temperature. I'll get this reaction to occur. And when the reaction occurs between the basic oxides and the siliceous material, the silicates or the boron silicates, the borosilicates, then I will get a salt. When you react an acid and a base, you get a salt. And we have a name for that salt, and you know what it is? It's glass. So we get a glass out of it. And that particular glass, we can, when we pour it out, it'll float to the top. We can hit it with a hammer, break the glass off, and I have a little lead pellet. And now with that lead pellet, I do something called cupellation, and I put it in a little cupel, a little boat. Used to be that in olden days, they'd make them all out of lamb's bones. They'd take animal bones, preferably young sheep, and they would dry, calcine the material, just heat it up until it pulverized, became like lime, and then squeeze it together, moisten it and squeeze it together and make a little cup out of it. It has a peculiar attribute, and that is, if you put this pellet of lead in it, put it back in the furnace, heat it up just below the melting point of gold, what you will find is that the material will oxidize. It's in an oxidizing furnace. The lead will oxidize, and the lead oxide will be absorbed by the cupel. It'll just drink it up like a sponge. And if you watched it, you'd find that the volume of molten metal keeps getting smaller and smaller and smaller, until all you have left is a little bead, and all of a sudden it would flash. Now that's called recoalescence. That's because all of a sudden it's given up its latent heat of fusion, right? And it gives it up so fast it makes a visible light. Now I extract from the furnace this little teeny bead that's gold. It has in it all the other materials that I can then, by normal quantitative analysis, a qualitative analysis, determine what else is in it, and by quantitative analysis, how much. And I can tell you how much we have in the ore. This particular process is known as cupellation, and cupellation occurs in mass. That is, we do refine gold by cupellation processes still, somewhere in the world. However, it doesn't sound very nice, because in one case, we're going to be spewing out lead oxides and sulfur dioxides. In the other case, we're going to have mercury fumes all over the place, right? So if you wanted to do that in near a well-populated community, well, you and the EPA are going to have a problem. So how would we do this in a modern way? It turns out that gold is a noble metal. All of these things are noble metals. They don't want to dissolve at all. They don't want to react with the atmosphere. They're not going to make any compounds. And so it's very difficult to get an acid treatment of them that will dissolve something. You can do it. There's one acid, by the way, that dissolves gold beautifully, and that acid is known as aqua regia. In fact, that's where it gets its name. Aqua for water and regia, noble, right? It'll dissolve gold. Aqua regia is a mixture of hydrochloric acid and nitric acid. It dissolves everything. Well, that's not going to do much for us in refining, because we'd have this material in solution. But something else that will dissolve gold and these noble metals is a material that we talked about when we did heat treatment, and that's cyanide. Sodium cyanide, potassium cyanide will dissolve gold. So we make aqueous solutions of the cyanides, and we take the ore that we have now, that we've beneficiated, and we put it in this solution, and it will dissolve all of the noble metals right out of the gangue material, and we can filter it and throw away the gangue material, the tailings, from this particular process, and have left a material that is going to be pregnant with the noble metals. But now it's all in a liquid form, and it's going to be hard to make rings and eyeglasses out of this material, right? So what are you going to do? Well, it turns out, as we will see when we study corrosion, that all you really have to do is to put something in that solution that is higher up in a table called the EMF series, and it'll plate out on that material. And such a material would be zinc and or aluminum. But do you remember when we talked about the diagram that was called a peritectic diagram? We said the reaction can only occur at the surface, and we have a little wall around. So now we have a situation where we put, say, zinc in the material, in this solution, the cyanide solution. We'll plate the gold out on the zinc. But where on the zinc? On the surface. And after that, then the solution only sees gold, and it won't plate out anymore. What does that tell us? That we have to have the thing that we add in tremendous areas of surface. That means we have to put it in as very, very fine powders. Stir it up, the gold plate soap, take the solution off, and now we've got the gold and zinc all mixed up together. Now what do we do with that? Well, it also is capable of being distilled off. Zinc has a very high vapor pressure, so we get it molten, get it up to 1600 degrees, and it boils like water of that order of magnitude, 1600 degrees Fahrenheit. And so we can just boil all the zinc off, we have the noble metals left behind. And so that's a process that's used. The zinc vapors are not as bad insofar as toxicity of poisoning as the mercury vapors, and so we have a process that's a durable process.
In order to extract gold from its ore, the ore must be beneficiated or transformed into a condition that will allow the gold to be extracted. Often this means physically breaking up the ore before further refinement can occur. Two refinement processes for gold are amalgamation refining and cupellation. In a less toxic gold refining process, aqueous solutions of potassium and sodium cyanide dissolve the gold, and gangue or debris is filtered out, and the gold is then recovered.
It doesn't make much difference where we're going to put our finger now. We're going to have a problem in having an ore of a material, unless it's noble. Then we're going to have to do things like this. We're going to have some sort of refining techniques that we have to look at. But for the moment, let's just take a look at what are some of the materials that we would like to examine. What are some of the materials that we would like to see a process for extracting them? Because all the processes are not going to be the processes like for the refinement of gold. Well, we have a great use for light materials, and of course one of these light materials is aluminum, and it was fortunate that that came along when it did, because if you look at your history book again, and it's always absolutely fascinating, if you look at your history book you find that we learned to make en masse great quantities of aluminum, and when we learned to do that it was just after the discovery of the dynamo, the thing that would allow us, the machine that would allow us to generate enormous amounts of electricity. And so back in the latter part of the 19th century, we found out these two things got coupled together, and we had the capability of making aluminum. And if you know your history, we turned the century, and a couple of guys from Ohio learned how to make an airplane fly, a lighter, heavier than air equipment. And one of the things they had to have was a metal that would make an engine that would be very lightweight. And so wasn't it fortunate that the aluminum had already come along? And these things, they almost look like they're planned the way they happened. But nevertheless, we've been looking for light metals that will do jobs for us. Now, we'll talk about aluminum more in detail but a little later, but we look at materials like beryllium and magnesium, titanium as materials that could substitute for aluminum. And when we find these things, we find that we have to do something different insofar as a manufacturing process is concerned to derive them, to produce them. So let's look at a couple of them to see what we have to do to win them. But let's, instead of concentrating severely on that, let's see what we would have once we get them, what would be different about it, why we would be interested in that. If you look at the aluminum, let's say, compared with steel, you find that aluminum has a modulus of elasticity of about 10 million. If you looked at steel, it has a modulus of elasticity of about 30 million. So as soon as you substitute aluminum for the steel, you're going to have something that has a lower modulus. Now maybe that doesn't make any difference to you in your design, maybe it does. But the maximum strength that we could get in the aluminum alloys is going to be something very low relative to what we can get in steel. We haven't succeeded in getting an aluminum alloy yet to say 500,000 psi, and we can do that, just barely do that, in a patented wire of steel. So we have to look at the properties that we can get, but generally we're faced with the problem of what is the strength and the volume of the material at the same time. Because we can take a lower strength material, increase its cross-sectional area, and carry the same load we could do with a material that has a higher strength with a smaller cross-sectional area. So we were interested in the weight-strength ratio of the materials. And if we look on a weight-strength ratio basis, then we find that an absolutely ideal material would be titanium. And it would sit between the aluminum and the steel in the modulus of elasticity. Its strength can go very, very high. If we could procure that material out of the earth and make it into a form that was usable, it would be a salvation to many of our strength-weight problems. By the same token, if we look at magnesium, and I believe its modulus of elasticity is as low as something like 8.5 or something like that, but we can get tensile strengths on that equivalent to those of aluminum by alloying, and yet it's a still lighter material than aluminum. So if we could squeeze that out of nature somehow and make use of it, then we would have made a big step forward in our design use. But how in the world are you going to get the magnesium? Well, number one, we're going to do it very similar to the way we get aluminum. In fact, we can get it in a much simpler way than we get aluminum, except that we're going to squeeze a lot of it out of seawater. And now, if you get the picture, what I'm trying to tell you is all the ore that we find is not out there in the form of what is just dirt. Here's a material that we actually mine the ocean water. In Corpus Christi, Texas, they pump the ocean right through an enormous system and take the magnesium out of the water and generate it into a form that's magnesium hydroxide. That's milk of magnesia by the multi-ton, if you can imagine that. And then they have to decompose that magnesium hydroxide into elemental magnesium. And so we can do that, and it's done to a process similar to the refining of aluminum, and I'll cover those both at the same time. Well, how about the titanium? It was for a long time very difficult to do, and we find that we couldn't do it by these particular processes that we use for aluminum, but we did learn how to do it, and we learned how to make it into a material, transform it chemically into something like titanium tetrachloride. And that particular material we can break down at proper temperature and pressure, so we can pass titanium tetrachloride over a hot wire and decompose it so the chlorine goes off and leaves the element behind on the wire, and we can get elemental titanium very easily. Very pure titanium this way, and we can win the material from nature. So in the search for weight-strength ratio materials, we've done, I think, fairly well, or pretty well, and we've come up with many, many alloys using magnesium, titanium, aluminum, and in fact, it's worth our time to see just some of the things we have done with titanium. For instance, today, one of the big uses for titanium is in military aircraft, or in aircraft in general. Costs a little bit of money, but it has capability of being used in an alloy form with titanium and aluminum. So a Ti-64, titanium 6% aluminum, 4% vanadium alloy is a material which can be made very, very ductile. So ductile, in fact, that we call it, in one condition, superplastic. And with that, we can make hexcell or equivalent hexcell material that we would normally use, you know, all of the little hollow honeycomb-like structures that we put a plate on either side to increase the rigidity of the whole member. And we can make those with a Ti-64 very easily. We can bond the material together very easily. We can make body implants out of these kinds of materials.